Hello everyone. Today I will be demonstrating the AI powered computer science e-learning platform. The goal of this project was to create a secure full stack educational environment that not only delivers curriculum but ensures students actually understand it using an integrated and hallucination free AI tutor. To achieve this, I engineered the platform on a modern high performance tech stack. For backend of this application, I used Fast API in Python to handle secure endpoints and orchestrate the AI logic. For front end of this project, I used user interface built with React.js. We have Wait build system and styled every portion of this project with the help of Tailwind CSS. And for database part, I utilize PostgreSQL to store user data, curriculum content, and progress tracking. Crucially, I heavily utilize the PG vector extension for semantic search capabilities. Now, let's dive into the user flow. The platform is completely gated by a secure authentication portal. Secure user registration and login endpoints are handled by using bcrypt password hashing and PYJWT for session tokens. I will log in now with my test credentials. Once authenticated, the React Router DOM handles navigation to this dashboard. The React dashboard dynamically fetches and beautifully renders available CS courses as tailwind cards. All of this content was automatically populated into the database using a robust seed.py script I wrote myself, which covers core topics like arrays, and other data structures, big O notations, complexity, BSTs, hash tables, and etc. like object oriented programming, DBMS, networking, and computer architecture. Let's get started. This is the custom lesson viewer. It features a split screen UI that utilizes React Markdown to properly format code snippet and mathematical notations. Because we are teaching computer science, standard text wasn't enough. All curriculum content is stored as raw markdown in PostgreSQL, and my front-end parses it in real time to beautifully format code blocks and math concepts like big O and big O square complexity, etc. The bottom of the lesson, you will notice a mark as completed button. This button is wired to protected backend tracking endpoint. When clicked, it securely hits the Fast API backend and updates the user progress table in the PostgreSQL to track exactly where the student is in the curriculum. Now here comes an interesting part. The core feature of this platform is the AI tutor. However, during development, the most significant engineering challenge I faced was hitting Cloud API region locks that blocked my AI embedding requests. Instead of giving up, I pivoted and engineered a custom hybrid RAG architecture. Let's give it some prompt. Can you explain how a binary search tree works? See, it has given the response in real time, and you can see here is exactly how this implementation works under the hood while the AI generates. Local embeddings. When a user asks a question, my fast API endpoint uses local sentence transformers agent to generate 384 dimensional embeddings. This happens entirely on my machine, bypassing cloud blocks. Another feature is vector search. It performs a cosine similarity search against PostgreSQL PG vector database to fetch relevant lesson context. Another important part is cloud generation. I used the cutting edge Google Gen I SDK to pass only that retrieved markdown context to Gemini 1.5 Flash model for answer the generation. Because it fetches the exact markdown context from the database, the AI provides highly accurate, context aware answers instantly. Now, here is another interesting part. What will happen if we give our AI tutor an out of the box question? I mean, the question that out of the scope of our content we have stored for our platform. What will happen in that case? A major issue with that case in with AI is in education is hallucination happens if the content is not present on our platform and a question arises to that AI agent for that content, then that AI might be hallucinate a lot. So to prevent this, a strict system prompts act as a guardrails, successfully forcing the AI to refuse to hallucinate information outside of my shaded curriculum. As you can see, the AI mathematically refuses to the answer to the out of the box question. Let's give him some out of the box question. Let's give it. See, I can only question based on the curriculum context provided. The curriculum does not contain information about the Super Bowl. Yeah, this is how hallucination is prevented. To implement this efficiently, I designed a hybrid database table. My once again. Okay, my lessons table acts as a hybrid holding both standard text data and PG vector embeddings in the exact same row. It holds standard data like title and raw markdown content. It also contains a content embedding vector column. When the cosine similarity search finds the closest mathematical match in the vector column, the backend instantly grabs the normal markdown text from that exact same row to feed to Gemini. Okay, but still there is question in my mind. How does embeddings are compared and stored? So to manage our curriculum and AI data efficiently, I implemented a hybrid table architecture in PostgreSQL. Instead of keeping the AI data in a completely separate vector database, a normal relational data and mathematical vector embedding live side by side directly inside the lessons table. I can show it. Here it is. The vector column. The table has normal columns to hold standard data such as the lesson ID, title, video URL and the raw markdown content. Alongside these, I added a dedicated vector column named content embedding. This specific column leverages the PostgreSQL PG vector extension to safely store the mathematical arrays. In my SQL alchemy models, it is defined specifically as a 384 dimensional vector to match our local sentence transformers model. This side-by-side storage design is what makes the hybrid RAG hybrid RAG architecture so fast and efficient. When a student asks a question, the Fast API backend performs a cosine similarity search directly on the content embedding column. Once it finds the closest mathematical match, it can instantly grab the normal markdown content text from that exact same row to feed to Gemini as context for the answer. Finally, I prioritized security throughout implementation. All API keys are strictly hidden in the local.env file, and GitHub push protection is enabled to prevent accidental secret leaks. I have successfully delivered a 100% functional end-to-end platform. It features a robust Fast API backend, a seamless React frontend, and a localized vector database, powering a secure, hallucination-free AI tutor. Thank you for your time, and I am happy to answer any questions about the implementation. Thank you.